Good afternoon. My name is Jean-Louis Briot. I'm the Spencer J. Buchanan Professor in the Department of Civil Engineering at Texas A&M University. It's my pleasure to welcome all of you to the third Buchanan Lecture, which will be delivered by Professor James K. Mitchell of Virginia Polytechnic Institute and State University on the topic of the role of soil mechanics in environmental geotechnics. You have a copy of the lecture. Note that this year we have included a list of contributors to the Buchanan Professorship. We did our best to make sure that we did not forget anyone. Please let me know if there are any errors or omissions. As I do each year, here's a short report on the finances and the use of the funds of the professorship. I received the professorship in 1992 when the corpus was at $640,000. In my acceptance speech, I established some goals, one of which was to reach $1 million by 1997. Today, the corpus of the professorship is at $960,000, and therefore we have almost reached our goal, thanks to you, the contributors, to the stock market, and to the fact that I put a significant amount of the interest back into the corpus. The Spencer J. Buchanan Professorship is now the largest professorship in the College of Engineering at Texas A&M University. I think our geotechnical engineering community should be proud of such an achievement. The yearly income varies from 3 to 5% of the corpus. This past year, the income was much smaller than usual because of the poor financial market. The money was used to support the second Buchanan Lecture, to continue our effort in bioremediation research, where we're analyzing the EPA database of case histories, and to increase our effort in expensive clays. This problem has a tremendous negative impact in College Station, in Texas, and throughout the world, yet research funding is quite limited because, unlike earthquake, hurricanes, floods, and other natural disasters, nobody dies. We're using the professorship funds to develop, in concert with industry, a radically different yet simple and practical approach to heave calculations, where the water content versus strain curve plays the role of the stress versus strain curve for loading problems. We plan to present our findings at the San Antonio meeting of the ASCE Texas section. I believe that unsaturated soil mechanics needs to be a major topic of research for the next 20 years, so that saturated, positive pore pressure soil mechanics can take its place within the larger framework of true soil mechanics. Indeed, soil mechanics is made of 3 separate fields: saturated positive pore pressure soil mechanics, that's the one which dominated our field for the last 70 years. Saturated negative pore pressure soil mechanics, that is the soil behavior in the capillary zone. And unsaturated soil mechanics, where we have a true 3-phase problem. Another goal that I established in 1992 was to create the Spencer J. Buchanan Lecture. I did that for several reasons. It gives us a chance to bring outstanding speakers to the state of Texas and to capture their thoughts on videotape for generations to come. Imagine for a second that you're a geotechnical engineer in the year 2100. And here is a videotape of Professor James K. Mitchell delivering a lecture. What a real treasure. I sure wish someone had done that when Terzaghi was around. This lecture also gives us an excuse to get together once a year and visit with good friends, and it does give nice exposure to our university and our program. As you may know, our 1993 Buchanan lecturer was Ralph Peck, who spoke on the coming of age of soil mechanics. Our 1994 speaker was Jeff Meyerhoff, who spoke on the evolution of safety factors in geotechnical limit state design. The 1995 Buchanan lecturer is Jim Mitchell, who will speak on the role of soil mechanics in environmental geotechnics. Hard copies and videotapes of their lectures are available. I have discovered one drawback with the Buchanan lecture, though. It does provide a very clear reference of how fast time goes by. It's like being on a narrow highway with closely spaced trees. You really think that you're going fast. While if you were in the desert at the same speed, you would think you were crawling. Since we have not yet found a way to stop time, we're going to have to live with that drawback. Immediately after this introduction, Dr. Anderson will give a short overview of our geotechnical program. Then Dr. Young will introduce Professor Mitchell. Following the lecture, Mr. Hooper, the leader behind this professorship, will lead the discussion, and as is our custom, Dr. Buchanan, the son of Professor Spencer J. Buchanan, will close the lecture, which will be followed by a reception and photo session. Now it is my pleasure to call on Dr. Glenn Anderson to tell you in about 20 minutes all about our geotechnical and geo-environmental program. We would appreciate your thoughts and comments. Glenn received his master's degree from MIT, where he worked with Bob Whitman on the behavior of retaining walls under earthquake loading and made use of the centrifuge during that study. He received his PhD degree also from MIT, where he worked with Chuck Ladd on the behavior of frozen soils. After a 2-year stay at Tulane University, he joined our group in September of this year. We're obviously very happy to have him among us. He is the new member on our team, Dr. Anderson.
Being the newest member and only having been here 2.5 months, it's quite a task to describe a geotechnical program that's been going on for many years. I'd like to take a few minutes and summarize what I've been able to learn in the last 2.5 months in terms of where we are today as a geotechnical program and present some goals for the future. And I hope that you enjoy my perspective being so new and obviously so uninformed of how everything works around here. In terms of the professors and researchers that have had an impact that are still among us, I was able to find the names of 10, 3 of which are officially retired, but some of them I believe I see more than some of the active professors. So we know that they're still very busy. The group consists primarily of professors that have been educated in the United States. There are 4 notable exceptions. Professor Briot, of course, from France and educated in Canada. Professor Morris, educated at Cambridge University in Cambridge, England. Professor Young, as his undergraduate in Hong Kong. And Professor Dunlap, who spent a period of time in London. As I looked through the list of interests and the backgrounds of all of the people in the program, it became apparent to me that I was the only person that didn't have a Doctor of Philosophy degree among the group. And as I further understood that Professor Mitchell also is a holder of a Doctor of Science from MIT, I thought it might be interesting. There may be some people here that don't understand what a Doctor of Science from MIT really means, and so maybe perhaps I can take a few moments and explain what it means to me. It's not in any way similar to the Doctor of Science at in European institutions, where a person receives a PhD and then after many years of distinguished service is awarded a Doctor of Science. At MIT, the Doctor of Science comes about as the student receives a small 3x5 card for the graduation, and there's a little box that you check whether or not you're going to receive a Doctor of Philosophy and a Doctor of Science. And you can imagine, my experience was, I can still remember to this day how I made that decision. It was a moment of deep personal reflection as I stood in the registrar's office with this card in my hand. And as I considered all of the different ramifications, it occurred to me that there were really just two factors that were playing a role. The first one being, did I feel that the research that I had done was more philosophically based or scientifically based? And that was kind of a hard decision to make, but the next one was a little more difficult. It was whether or not I wanted to have a doctoral hood with a dark, deep purple band around the outside that actually blends quite well with the black robe so that you can't really see it, or whether I wanted to have a bright yellow band on my doctoral robe. Of course, with the bright yellow band, it could come in handy later on. It's safety related because you never know when you may be called upon to march in an academic procession in the middle of the night across a busy intersection. At any rate, as I went through the interests, you can see that they are quite varied, covering every major aspect of soil mechanics, I believe. And what I'd like to do now is talk a little bit about what are the academic responsibilities that we have amongst these professors. In terms of the undergraduate program, there are three courses that are offered. One of them required, the Introduction to Geotechnical Engineering, through which approximately 300 undergraduate students pass each year. Another course in geotechnical design, and another course in case histories, where I presume many of the former students have come back and actually presented case histories of events. In addition to the geotechnical courses, we're also required to offer some service courses to help out the College of Engineering, and I've given a few examples there. In terms of the graduate program, we're currently under revision, and so I haven't listed courses by topic or by name, but rather I've made a partial list of topics that we think may be important. The reason why we're under revision is because the entire College of Engineering, and I guess more particularly the Department of Civil Engineering, has recognized that we are offering an enormous number of courses that aren't being given on a regular basis. The reason for that is that as they bring newer faculty in, they've increased the demand for performing research, and as a result, you need to decrease the demand for teaching. At any rate, this is a partial list, and one of the topic areas, I think, most of them are fairly standard geotechnical topic areas, but one that Professor Brio touched on was the partially saturated soil mechanics area. And we are very fortunate in terms of our program here at Texas A&M to have one of the eminent researchers in the field of partially saturated soil mechanics among us. And so I think we're, and that of course is Professor Litton, and I think that we're very well postured as we restructure our graduate program to offer perhaps one of a very competitive curriculum to our graduate students. In terms of the academic load, and I understand that these numbers here, it depends on who's talking to who, which numbers are given. As a new faculty member coming into the program, I've been told that a full-time academic load is 6 courses per year, and that the department will subsidize 1/3 of that load in terms of research. In other words, that I'm expected to teach 2 courses a year. If there comes a point in time where the research load is too heavy, then we have the option of buying courses with research projects. Now, I've talked to some of the senior professors here, and when I told them about the full-time academic load being 6 courses, they said, no, it's more like 8. So it depends on what end of the spectrum you're on as to where you fit. In terms of the contribution that the Civil Engineering Department has made to our geotechnical program, I was able to get some statistics. This unfortunately doesn't include all of the monies that have been given to support geotechnical activities, but rather the money that's been given to the Constructed Facilities Division. In the area of the undergraduate curriculum, approximately $20,000 this last year was spent on building another experiment station and other equipment for our undergraduate course. In terms of the graduate laboratory, approximately $53,000 has been spent to date, which involves a major modernization of the laboratory. We've purchased a centralized data acquisition system. We have now 4 Pentium PCs, 2 Power PCs. The Pentiums are, 3 of them are still on order. We've been supported in developing experiment stations in our graduate laboratory class, where we have been authorized to purchase a triaxial cell, which we will modify to make it state-of-the-art. And we have an HP laser printer now for the students. They're very happy about that. Additional support for the graduate students has included this partial support for the Buchanan student, Phyllis McAdoo. And then in terms of faculty support, we've been given a Pentium, a 486 PC, a laser printer, and Professor Morris is on developmental leave and travel this year in Cambridge, England. So the bottom line, I feel, is that the department has been exceptionally generous with us in terms of our program and helping to support our activities. The next few slides, what I'd like to do is briefly go over a few of the research projects that are either ongoing or have recently terminated to give you a feel for the type of research that's being accomplished in the department. This first project, perhaps many of you will recognize as being a spread footing test, a spread footing load test at the National Geotechnical site under the direction of Dr. Brio. One of the hallmarks of the research here is very large-scale testing in the field. This next slide is representative of a process that Professor Young has been working with in terms of extracting contaminants from fine-grained soils using a process called electrokinetic extraction. I believe a process that he learned at Berkeley under the direction of Professor Mitchell. The next slide is representative of a moisture barrier that prevents the migration of moisture into and out of the soils underneath an existing pavement to prevent the heave and collapse of the pavement and the eventual breaking up. Our Professor Litton has been working for many years on partially saturated soil mechanics and has developed analytical tools which allow him to predict the performance of such a barrier in terms of its depth beneath the roadbed. The next slide is a picture of hydrates taken from the Gulf of Mexico. Professor Dunlap and Professor Brio have completed a project looking at the identification and the measurement of performance of hydrates in the Gulf of Mexico sediments. Of course, for the oil industry, that's a major problem when they try to drill a well and bring hot oil through the hydrates. They get a phase change, release of gas, and it becomes a real problem in terms of foundations. And finally, we're completing a centrifuge modeling experiment looking at the fundamental behavior of a retaining wall in an earthquake. And this is a side view of an instrumented wall that was built, calibrated, verified, and tested at the Rensselaer Polytechnic Institute Geotechnical Centrifuge, and that is capable of measuring interaction forces in terms of the orientation, magnitude, and position along all interaction faces, the backfill, the base, and the toe soils. In order to talk about the future, the first thing we need to mention is that our department has set a goal that they would like to become recognized nationally as a top 5 program. The last rankings that came out, we were about number 12, and they would like to up the ante and get into the top 5. In order to do that, we have to recognize the nature of the Department of Civil Engineering and understand a process that perhaps can help us get to that goal. Of course, I believe as a civil engineering department, because there are so many different disciplines, that we stand at a crossroads, and it's very possible that if we start all marching along our own paths, that we can diverge and not really accomplish anything. Fortunately, we have been given some direction, and we have mechanisms in place that help us to unify our approaches. And in the future, I believe that the most significant advances that are going to occur, at least in my tenure as a professor, will be in terms of solving large, complicated problems through integrated research projects. And what we have been challenged to do by our department head is to look at each of the divisions. In civil engineering, we have the constructed facilities, ocean and water resources, and infrastructure and transportation, and look to centers of excellence or centers of research that would allow us to do interdisciplinary interaction in terms of, for instance, there's a Center for Infrastructure Engineering that's headed by Professor Litton that provides an opportunity, or that can provide an opportunity for us to interact, the geotechnical people interacting with structures, interacting with water resources, infrastructure, and transportation. The purpose there is to cut across the divisional barriers and to start marching in some common directions. If we do that, we certainly can improve the already high quality of our program. In terms of the geotechnical contribution to the goal of getting ourselves into the top 5, I've listed 5 potential ways that we can do that. The first one being that every bit of research that's accomplished in our university should be published in a national or international journal that's refereed by our peers. The next thing that we can do is we can go after research projects that are nationally competitive, meaning that if we want to break into this top 5 and there's a professor there that's submitting a proposal, that we stand toe-to-toe with that person and get funded in some cases in front of that person. In terms of our theses and dissertations, they should be competitive. We should be able to take a PhD thesis from the Department of Civil Engineering at Texas A&M and put it right next to one from MIT, and there should be no difference in terms of the content, merit, or effort. And that's something that will make us competitive. We would like to see all of our Texas A&M University graduates be shortlisted on all of the top industrial and academic search and promotion committees, so that if ever there's a decision being made about who to be promoted or who to be hired, that we have an A&M graduate standing right there and competing toe-to-toe with the others. And finally, from my own perspective, we'd like to make our laboratory, our geotechnical laboratory, state-of-the-art. In order to do that, I think that we all have to recognize that sometimes there's a tendency for people to want to pull at a very small pot. And of course, when we get in a tug-of-war, we divide into 2 camps and the rope breaks and we both fall down. Really what we need to do is we need to pull together, we need to cooperate and recognize the contributions and the talents of each other and work in a synergistic environment. And I believe that that's entirely possible. Finally, if we do all of those things, I hope that someday I can be affiliated with the Texas A&M University Department of Civil Engineering that is truly a top academic institution. Thank you.
One of my dreams come true today as I was given the chance to introduce Professor James Mitchell, my professor at Berkeley, my dissertation advisor, and most important, a close friend. Following a relatively short but proud tradition of the Buchanan lecture series, this year's Buchanan lecturer does not need much introduction. Most of you know Dr. Mitchell by his research, his publications, his book, and his service to the profession. Therefore, I'm not going to read his resume to you, otherwise you don't have time to listen to him. Instead, what I'm trying to do is try to tell you something about Jim Mitchell from my personal experience. I came to know Jim by his publication 1981 when I was a senior in civil engineering at the University of Hong Kong. Thanks to a computer lottery, and they gave me a thesis title, Dynamic Consolidation. Honestly, at that point, I don't even understand the title. So I need to go to the library and do the search, and that's the first paper I found. It's the in-paste treatment of foundation soil, published in 1970 by Dr. Mitchell. And that paper opened my eyes in geotechnical engineering, and that dragged me into soil improvement and ground modification. So in 1984, I chose to go to Berkeley, even though I was given a chance to go to any university in the world if I want to on a voluntary scholarship. And this is probably the best decision I ever made in my life. I took Jim's course in my first semester on soil behavior, and the way he teach and the attitude towards students really changed my image about a professor. Because at one point I was educated in a business system. I think professor someone high in the sky and he's God. But the way Jim teach really changed the image. He's funny, very approachable, and he worked very closely with the student in the lab. So in 1985, it was my good fortune to become part of a research group, and most other students call us Mitchell's baby. And Dr. Mitchell makes you think all the time and seldom tell you what to do unless you are doing something terribly wrong. And moreover, I learned a lot from him by watching him closely. And from him, I learned a lot in geotechnical and geoenvironmental engineering. And I also forgot a lot of technical details anyway. But however, the most important thing I learned from him is his honesty, integrity, and the respect he paid to the others. One of the most important things I learned from him is a preposition. A professor, a student work with a professor, not for a professor. He respects his student very much and make use of every opportunity to make sure they can achieve full potential in their career. He seldom call you on the phone from his office. And in the summer of 1986, I developed a waste management database program for one of his research projects. And he asked me in my office, "Do you have a few minutes to teach me how to use it?" And one day in his office, he showed me a paper and asked me whether I may be interested to review it. And I say, yeah. And he immediately called the editor and get his permission to make sure I can become the reviewer for that particular paper. One morning in the spring of 1987, he walked into my office, as usual, shook my hand, and say, "We got it," referring to a Earth Technology Corporation fellowship we received from the company. And that's the very first time Berkeley won that fellowship. Another morning in the spring of 89, again, he walked into my lab. I was still working in my lab for my PhD, and say, "Guess what I have done to you?" I asked, "What?" And they say, "I gave your name as a student speaker for the upcoming industrial relation program for the College of Engineering. And in that particular year, that was the very first time student speakers are included on that important annual program for the college. Probably due to my own Oriental tradition, I always consider I'm a student of Dr. Mitchell and not a former student. And he always cared. And when I moved in Boston in 1981 to take up my first academic job, he wrote in his first letter to me, "How do you like on the other side of the podium?" That statement reminds me something very important now is my responsibility as a professor. And when my son was born last year, and he and Bernie sent me the first gift from our town. And when he learned my mom passed away earlier this year, he immediately sent me a note of sympathy through the email. No problem is too small to be analyzed, and no student is unimportant to him. One day, another graduate student and myself were waiting outside his office and tried to discuss our research progress with him. And he was explaining the concept of void ratio to an undergraduate student in detail while we were waiting in his office. My buddy and I got a little bit upset, and we say, the students should go to talk to this TA and not to bother Professor Mitchell for that small problem. And now, both of us now become professors. And at this point, we both understand we were both wrong then. That's the important part of professors to teach your student. And it's probably the patience and the respect of Dr. Mitchell for that particular student. She's working towards his PhD in geotechnical engineering at Berkeley. And most of the time, he has given his student more than a fair share of the research credit. In the acknowledgement of his 31st ranking lecture, he wrote, "I am especially indebted to a number of former and present graduate students who choose to undertake research with me on flow process in clay. Not only did they simulate and sustain my interest in these problems, but they taught me most of what I know and have attempted to communicate in this lecture." My Berkeley ring just has gained some more weight, as the graduate program at Berkeley has just been ranked #1 by a recent survey conducted by the National Research Council. While material resources are still very limited at Berkeley at this point because of the financial crisis in California, I strongly believe it's the character, integrity, honesty, and technical competence of faculty members such as Professor Mitchell that bring the program to #1. Without these important characteristics of the faculty or administrators, I do not think any program can reach the top 5. This introduction will not be complete without mentioning Mrs. Mitchell, and she's with us today. Every year, we have a small gathering at Dr. Mitchell's house. And Mrs. Mitchell prepares excellent dinner for us every year. For a foreign student like myself, who is about 9,000 miles away from home, and that meal is probably the best home-cooked meal for the year. And she designed games, and we talk over the night. She just want to make sure everyone of us have an enjoyable evening. They make us feel like we have a home away from home. I can go on and on, but however, I know you all come here to listen to Professor Mitchell. Jim, the only regret I have today is I have to introduce you as a professor at Virginia Tech. And without further delay, I would like to ask Professor James Kenneth Mitchell to present the third Spencer J. Buchanan lecture, The Role of Soil Mechanics in Environmental Geotechnics. Jim.
Wow. Where do I start? Thank you so much. It's very moving, and I'm grateful to you, Albert. Let me say that without students like Albert, and I'm sure the same is true here at Texas A&M, there would be no stories to tell such as he told. And I'm delighted, if I might just digress just a moment, to see Leonard Krasinski, who was one of our first students out in California, sitting in the audience. And it's truly a great pleasure to be here, to be with you. I'm honored to be here. I am daunted in the presence of the gentleman that you see on your left, whose memory we honor today. And I'm appreciative of all the good things that have personally happened to me in the career of geotechnical engineering since I got into it. I might note that of the people that have figured prominently in this Spencer J. Buchanan lecture, I perhaps knew Spencer Buchanan the least well. In fact, I don't believe that I knew him at all except from a distance, where I saw him at perhaps one or two occasions with his 10-gallon Texas hat and his tall, impressive figure moving about in the conference that we were both attending. I do know from the introductory remarks that were made at the inauguration of the Spencer Buchanan lecture that he did indeed create, achieve, and leave a legacy of a very great deal. I listened to how he organized the Corps of Engineers geotechnical work, started the laboratory at Vicksburg, did so much during the war years in military roads, airfields, and the like, came here and started the program, developed his own company, which is highly recognized all over, and say to myself, my heavens, to be able to do just one of those things well would be a remarkable achievement. And this man, Spencer Buchanan, did them all. I wish that I had known him personally. I did know Carl Terzaghi. He didn't know me, I don't think, but I took a course from him at Harvard. When I was a student at MIT, we could go to Harvard and take courses. and I took his course in engineering geology, which was truly a remarkable experience, which I will always treasure. I also was able to put my foot out at the wrong time on a tour boat cruise in Switzerland at the time of the Third International Conference and trip Carl Terzaghi as he walked by. Fortunately, there was no permanent damage. I have been privileged also to work with both Ralph Peck and Jeff Meyerhoff, your first two Buchanan lectures. I have seen them each within the past few months, both doing very well, vigorous, active in their various projects. It's always great fun to see them. And this morning, I was able to spend an hour and a half with the graduate students in the geotechnical program here at Texas A&M. That was truly a great, fun time for me. I don't know why, but when I have the opportunity to sit with a group of students that way and talk about what they're interested in and try and answer their questions, and they ask very many penetrating questions that I can't provide good answers for, but it's fun to try, I really enjoy those types of experiences. And now hearing about the development of your program and seeing your aspirations, I'm quickly coming to the conclusion that you'll be there. You'll be one of these, first the number 5 and then moving towards the number 1. And I admire what I see going on here and the way it's being done. I would say this one thing about what Glenn was saying about the SCD from MIT. It has really changed. It's loosened up at MIT. Their standards evidently have changed because I had no choice. In civil engineering, you were awarded the SCD. There were no cards, there were nothing. And in fact, you are right about the hood, and had I, on my graduation day, been at the graduation instead of in basic training in the U.S. Army at Fort Jackson, South Carolina, I would have gotten one of those nice hoods, which I subsequently had to buy. I would have gotten it free if I'd been at my own graduation, but that didn't work out. In any event, the title of my presentation, which you, I think, already have copies of, is Soil Mechanics and Environmental Geotechnics. And before I get into the meat of this, I just want to tell you about a little-known event that happened back during the Apollo program days. Now, something that you perhaps will see if you read the biographical stuff that they put into the publication here. I was pretty much involved in the lunar exploration program during the Apollo years, and so I spent a lot of time at Houston, both working on the things that were going on the moon, and also with some of the samples that were returned. And if you may remember, back to 1969, the first samples were returned to the moon. Many of them were sent out for analysis at universities all over the world, actually. And there was only a small amount of material that was set aside for that purpose, but yet these analyses were done. And the allocation of these was the responsibility of one of the scientific teams, and the final distribution was made by the curator of the Lunar Receiving Laboratory over in Houston. He'd made the distribution of the amounts that could be distributed, and a letter arrived one day. It came from a university, Texas A&M. And the letter said, "Heretofore, we have been largely a teaching institution, but we are now making major advances in research and development. We have expert people in all fields, and we are quite disappointed that we have not been allocated a sample of lunar soil for the studies. We would appreciate it very much if you would send us for some material for us to use in our analyses." And the people at NASA headquarters were really concerned about this because, after all, NASA's budget is federal money, taxpayer money. It's the state of Texas. Texas A&M is the state of Texas. Lyndon Johnson was much involved in all these kind of things, and they had to keep the constituency happy. They said, "What are we going to do? We can't allocate any more of our sample. We just are not allowed to do that." Well, one enterprising individual says, "Look, these guys over there can't figure it all out that fast. Look where we are. We're here in Texas, and look at all these fields and all the stuff that we got lying out there in the fields with all these cattle around and everything else." And they said, "You know, dried and pulverized, the color's about right and everything else. We'll send them a sample." and we'll see what happens. Well, about 2 months, 3 months went by, maybe even a little bit longer. A letter came back. It said to the curator and the Lunar Science Sample Analysis team, we are pleased to report that we have now completed our thorough and most exhaustive tests on the sample of lunar material which you sent us, and we can report the following. The cow did jump over the moon. Well, what that means, if we tie it to today's subject, which is environmental geotechnics, that when all the sites are cleaned up here, there will be plenty of work to do yet up on the moon. Not only from that source, but because of all the debris that was left behind by the astronauts and the non-manned lunar vehicles that were left on the surface of the moon. What I would like to try and do in the time that we have together is talk a little bit about the role of soil mechanics in environmental geotechnics. Environmental geotechnics forms a part of what we might call geo-environmental engineering. I'd like to begin with a couple of definitions about all of this, because this is an area of our activity these days that is very, very dominant. And in fact, we hear all the time about the environment and about cleaning the environment and the safe disposal and storage of waste and all these kinds of things. And we hear the term geo-environmental engineering wherever we go. Seems to me that geo-environmental engineering really is concerned with the overall engineering of environmental projects. Environmental engineers sometimes think that we're trying to tromp on their turf in the things that we do. I don't believe that's true at all. I think that what we as geotechnical people do is environmental geotechnics. This is the geotechnical engineering for environmental control. It is a much more focused, a much more specific thing than the overall engineering of the environment. I think all geotechnical engineering, all engineering on, in, and with the earth should be environmental engineering. I would like to see the day come when we don't have to use that kind of a term. It's just accepted that whatever we do will be done with a sensitivity towards the environment and its protection. But I think that there will be always a role for environmental geotechnics, which is the specifics of what we do as specialists in the geotechnical field to achieve these goals of enhancing, protecting, cleaning, whatever, the environment. And I think that's an important distinction. It is a component of geotechnical engineering, and it's a component that I want to focus on here in this presentation this afternoon. It seems to me that we have a number of applications of things that we can do well, a number of things that come up in the environmental problems that involve strength and stability of the ground, settlement, deformation, seepage barriers, all of these kinds of things where we are going to be applying soil, waste, and geosynthetics mechanics. And it's this kind of mechanics that I would like to elaborate on a bit. There are a number of kinds of projects that seem to be the ones that dominate in the environmental geotechnical field: the design, construction, and the operation of new waste disposal and waste containment facilities, the isolation of contaminated ground, and the remediation of contaminated sites. And the whole point of what I am trying to get across in this third Buchanan lecture is that soil mechanics is important in all of these. I could stop here, and my message, if it were completely absorbed and reflected upon, would be over. But I want to elaborate a bit on it, and to show you by means of illustration before we're finished why soil mechanics is important in all of those things. Now, first, to give you an illustration of these kinds of projects, here is a new waste disposal project. This happens to be the Keller Canyon Landfill, which is located in the county in which I used to live in California, and it's a new municipal waste disposal facility. It was completed about 2 or 3 years ago. For isolation and containment of contaminated sites, we often use things like slurry wall cutoffs, such as you see here. For remediation of the environment, we might use some sort of an in situ biological treatment, or we might use an electrokinetic technique of the type that Albert is involved in here in his research at Texas A&M. So these are the three of the kinds of projects that we deal with in our work. If we turn our attention to landfills, which certainly occupy the time and use the talents of many of our geotechnical colleagues, we have different kinds of landfills. This is just a schematic of a waste pile with a cover over the top, the original ground surface, and one has to be concerned about containing things safely in here. There are a number of problems associated with their design, construction, closure, long-term maintenance, and so on. This happens to be a very large above-ground landfill located in the center of Los Angeles. Currently the subject of a great deal of study. I'll tell you more about that later. Other kinds of landfill repositories are in the grounds, such as you see here. And here is an illustration of a Class 1 hazardous waste landfill located in Central California. I'll have a little bit more to say about this one as well. The waste is piled in here, contained within a lined, carefully designed and lined repository system. We have a number of concerns with these waste landfills. We must contain the leachate. We must prevent surface water infiltration, maintain stability, and resist seismic shaking. You may think of some others, but we'll be looking at a few of these. The landfill requirements have evolved very significantly over a 10-year period shown on this slide from 1981 to 1991. And if you would look at this, it's waste over filter soil, over gravel with a perforated pipe, over clay, over subsoil. You can't do things that simply anymore. And even this is complicated compared to what I remember as a kid, where you had a town dump. By 1991, we were looking at complex composite systems here of geosynthetics and compacted clay and collection and drainage systems and so on and so forth, not only once but twice within a landfill liner, according to some legislative requirements. So there has been a real development into more complex engineered systems for lining landfills. Similarly, for covering landfills, we have to turn our attention to what would make a good cover. And in this cover, before you even get to the waste, which is down here, you have some soil cover, a geomembrane to keep the water out, a bedding layer, a drainage layer to help things drain away, a filter to keep things from mixing up, a topsoil layer so that you can grow things on the top and go away and leave a suitable facility when all is closed up and said and done. One of the main problems that we have to deal with in landfills nowadays is that of the stability of different parts of the facility. And this is simply a list of the kinds of failures that can occur in modern landfills, or existing old landfills for that matter. And I'll just show you by means of simple sketches what I mean. Sidewall slope and base failure. When you have an excavation here, while the excavation is open, of course, it's possible to have this type of a stability failure or a superficial failure of the form that you see here. We have to worry about the pull-out of liner components that are coming down the side of our slope into the waste repository area, which would be over here. And this could pull out of the trench and so on and go on down the slope. There are techniques for designing against that type of failure. We could have failure through the waste fill itself, such as you show schematically here. The failure could be more complex, coming through the waste fill, through the base liner, through the foundation, and so on. There's many variations on this possibility. It wasn't always that these kinds of stability considerations were taken fully into account, and you're going to see the consequences of that in one of the examples that I will be showing you. It's an example showing this kind of a stability failure here, where the waste pile actually slides simply because it gets too high. And it can't be resisted by the resistance along the bottom of the lining system, and it moves and causes a failure. Those are the types of things that we have with landfills. And we've chosen these kinds of things some cases of those kinds of systems for examination of the role of soil mechanics. We have looked also at some concerns with tailings dams, because these are important geotechnical structures as well in many parts of the world. And we have a number of issues that are of concern here relating to the foundation support, the seepage, the stability under static and seismic loads, and so on. And in a tailings structure, there can be a number of things that we will have to look at. If this is the tailings dam embankment here, we have to be concerned about the stability of that embankment. We're concerned about the seepage through that embankment. We are concerned about potential creep deformations in the foundation. I know of a case where these are important. What about the overall stability of the foundation? How about the consolidation of the tailings? Generally, we want them to consolidate for at least two reasons. One being they become stronger and thereby reduce stability concerns. Another is that by consolidating, you gain more airspace above and you can dispose more tailings, both of which are important considerations then. And in seismic areas, which seem to be very often associated with, seismic conditions are very often associated with the locations where mine tailings operations are in progress, we have to be concerned about the liquefaction there and the potential consequences on the structure, the overall stability of everything. So there are a lot of environmental concerns in dealing with tailings facilities, and many of these involve soil mechanics issues. A third category of environmental type of problem that we as geotechnical folks get ourselves much involved with is the in situ isolation and containment, safe containment of waste in the ground. And barrier systems of various types now are available. They can be built. We need to know about their characteristics. We need to know how perfect or imperfect they are as barriers against seepage flow out, seepage flow in. We get concerned about the bottom, whether we can use a natural bottom or have to put in an artificial bottom. We have to be concerned with the cover and all of these things to be sure that we indeed can safely contain the waste in the ground. It's quite a technology in itself. This is an interesting photograph. This happens to be the present day appearance of Love Canal in Niagara Falls, where much of what we are into now has its origins. If you recall a bit of history, back when all the ground pollution was discovered here in the Love Canal area of Niagara Falls, people were getting sick. It was Hooker Chemical Company was involved in all of this. They did massive restorations of the area. They had to move people out, clean things up. Now they have it contained. This is a modern cover over the area that was most contaminated. Leachate is pulled out of this and it's treated in this facility over here. So this is a historical project from the standpoint of moving things in a particular direction for environmental regulation, environmental control. In these issues of isolation of the contaminated ground, we have a number of concerns. Slurry trench stabilities, properties of soil and cement-based barrier materials, stresses and deformations in and next to barrier walls and covers, seepage and contaminant transport through the walls, the floors, and the covers. So these are things that the geotechnical people are uniquely qualified to deal with. So there is a lot of soil mechanics to be dealt with there. And I'm going to try and illustrate by means of several examples the kinds of issues that arise that require that we need to do as good soil mechanics in solving these problems, interpreting what's going on, making predictions and the like, as for any other kind of geotechnical engineering. And I'm going to do this by, as I've indicated, generally speaking, by means of considering landfills and some tailings dams issue with a couple of other things in there that don't really fit in those categories. Before I do that, though, I just want to say one thing. I'm not going to, in this talk, be dealing with material properties as such in any detail. That's not to say that I don't consider them important. In fact, I would say that the two most important things that you're going to have to deal with in any of these kinds of problems are the site characterization and the properties of the materials themselves. If you don't do that right, anything else in the way of analysis will be absolutely meaningless. But always properties are important here. Just as in our teaching of geotechnical subjects, we must spend a third to a half of our time talking about the properties of the soils and how to measure them, how to express them, how to deal with them in analysis, and so on and so forth. And we have to do that because the soils are so vast and variable in their characteristics and the ranges of materials that we can run into. It's not like working with cement or with concrete or steel or any of those things that we can pretty much design to specification. So always keep in mind the importance of properties. Well, I would like to show you a couple of aspects of these two things that relate to the strength and stability analyses and their importance in environmental geotechnics. I'd like first to say a little bit about this landfill here, which is the Kettleman Hills Unit B19 Phase 1 of a hazardous waste facility in Central California. What you're looking at is a waste pile photographed about 4 days before it failed by means of a translation in this direction of about 35 feet, a settlement back up here of about 15 feet, and a complete disruption of the lining system, as you will see, I think, in one of the slides. And note the shape of this runoff retention pond down here. I'll show you in another slide. You'll see how it's distorted. It'll give you some perspective on this. This waste pile is about 100 feet high. It was about 100 feet high. It covers, I can't remember the number of acres, but you will see it on a slide. This side slope is a 3-to-1. This is a 2-to-1, and that's a 2-to-1 in the back, just so you'll have some appreciation for the geometry. It's 50,000 square meters. The fill depth was 30 meters. The side slopes, the toe slopes, was 3-to-1, and a nearly level planar base. It had about a 2% slope towards collection sumps for leachate in the base. It failed in March of 1988 by 1988 by sliding, and you can see how everything is pulled down. It moved from your right to your left about 35 feet. It happened over a period of something of the order of 5-6 hours on a Saturday morning, and was not catastrophic in terms of loss of life, but in terms of compromising the integrity of the lining system and those kinds of things. It was a very important event. It's had a major impact on how we do landfills. If you look across here, you can see some cracking and so on. Trying to figure out the cause of this failure required looking at an awful lot of things in this particular system. You can see in this slide how the surface cover liner was, it's a lining over the base liner that's just distorted right here, and it moved in that direction through the valley. And the lining system at this particular facility was a very complicated thing designed to current state-of-the-art standards and regulatory standards. Down here is a VADO zone monitoring system. It's in the paper, so I'll just go quickly over this. The secondary clay liner here with a high-density polyethylene flexible membrane layer here, so it's a composite liner. The membrane over the clay. Drainage collection removal system here. Primary clay composite liner up here, primary composite liner, compacted clay, 1.5 millimeter thick HDPE right here. And so you see this is a real belt and suspenders operation with a double composite liner system for the leachate collection, removal, and so on. And then finally up here, the waste is collected on top of everything. As the investigation finally resolved itself, we know that the sliding took place right here. The sliding in the base of this repository took right here, between the secondary FML, or the HDPE up here, and the compacted clay. Of course, we couldn't know that at the beginning. All we could be reasonably sure of was that it probably slid somewhere in the lining system. This is simply a contour diagram of the waste itself before it failed and after it failed. And you can look at the topography. They're in the written version, and you can see what these were, and they pretty much support the movements that I told you about. Okay, now trying to unravel the mysteries of how this failed and why it failed led us to an explanation which was basically correct in terms of how it slid, where it slid and the like, but you couldn't be sure till they excavated all the waste out of the repository and moved it somewhere else. And that took a couple of years after the failure. And we wanted to learn about the mechanics of this kind of a failure. One of the things that we got involved in was building models. And this is a model of that waste repository. And if you look at this, you can see that after failure, the cracking on the surface is very much the same as it was in the earlier photograph taken from the air of the actual facility. And by scaling the model properly, we found that it would reproduce the behavior very well. By having some marker beds within the structure, we could learn something about the internal configuration of things and develop a model for the stability analysis of this. But you might ask yourself, how will we analyze the stability of this? We're used to using a two-dimensional cross-section of some sort to do the stability analysis. Where will you take that section? Where you take that section becomes critically important. Or should we look at the whole thing as a three-dimensional mass? We had to consider all of that, and in the end, it was necessary to do some three-dimensional analyses and resolve the issues and get some idea of how well they compared with the two-dimensional results. But basically what you're looking at is a situation where you have a waste pile with this configuration, and these blocks of waste are sliding down. There's waste that sits in the bottom on top of the liner, which is a passive block which is holding it back, and you have things coming down from the rear, sliding in from the side, and so on, all pushing on this. In the end, the vinyl analysis showed us that simply the pile of waste got too high and the driving forces exceeded the resisting forces. And of course, you don't have to be a rocket scientist to know that things fail when the resisting forces aren't as great as the driving forces. But still, writing it all or analyzing it all in a quantitatively satisfactory manner was a bit of a challenge. But basically, looking at this thing in plan, you have waste coming down the slope, waste coming down the slope, waste coming down the slope, and this block in here resisting it. And there are configurations, there are geometries when these forces just simply overwhelm these forces and the thing slides. And so when you have a repository with diverging side slopes, as was the case here, you can have a critical three-dimensional case that leads to failure. Well, without going into the details of that failure, we can draw certain conclusions that are important to us in dealing with the stability of waste repositories. And let me say that in the written version, we were careful to include references to all of these things so that anybody who is interested in pursuing any of the subjects in further detail, you can find them in the references. And for those who are interested in this subject in general and for students, we've tried to include references to fairly recent publications that are comprehensive, that provide an entree into a vast array of relevant previous literature. So hopefully that will be helpful. The other thing that I should mention is that I do have a co-author in this work, and I should have mentioned his name previously. That's my colleague George Fills, also at Virginia Tech, and he and I collaborated in putting some of this together. Otherwise, it wouldn't have been possible within the time that we had to get some of this stuff up and going to have done the complete story. Well, let me tell you what some of the conclusions were from our analysis of the Kettleman Hills situation. It slid, and the main cause was that increasing the height of the waste reduced the factor of safety below 1. There were no earthquakes, there were no rainstorms, there were none of those kinds of things. It was simply the pile got too high. We had a lot of uncertainty in our initial analyses, and that led us to do model tests, which reproduced the behavior, clarified the mechanisms very nicely. We developed a new 3D stability analysis method, which predicted both the model and field behavior. And that is a method for 3D analysis that is limited to analyzing waste masses that are on defined sliding surfaces. You can't do a general search for a critical surface, but if you know where the sliding is likely to take place, you can do the analysis with this program. We certainly learned all about low interface strengths in liners, and this is an important thing that I think was focused on as a result of this work, that Before the Kettleman Hills failure in 1988, concern in landfill liner systems seemed to be with low hydraulic conductivity. Keep the hydraulic conductivity low. So you compact the clay, wet of optimum moisture content to get the low hydraulic conductivity, but when you do that, what you get is low strength too. It's an optimum for hydraulic conductivity, and it's one of the worst places to compact it for strength considerations. And when you're dealing with clay, compacted wet of optimum, or geosynthetic liners with geogrids and flexible membrane layers and things of that sort, you're dealing with material with very low friction angles, down as low as 8 degrees or so. And remember, the side slopes in this landfill repository were up to 26.7 degrees on that 2-to-1 slope. We found this condition relative to geometries and stability. Typically, the two-dimensional analysis will be okay unless you have divergent side slopes, in which case you can have lower 2D factors of safety than 3D. So if you're looking at a situation like that, be conservative if you're going to base a design on a 2D analysis. And these things, I think, now are fairly obvious, as shown here. So those are some of the things that we learned about from Kettleman Hills. Now let's turn our attention to a tailings dam failure, a limit equilibrium analysis situation where soil mechanics limiting equilibrium would have paid rich dividends. And I hope you forgive me if I read some of these things. We took the liberty in finding illustrations not totally from our own experience, but including also some relevant cases in the literature. And this happens to be one of those cases. The Prestival Tailings dams failed in July of 1985, and these are in northern Italy. And the case shows pretty much by omission the importance of soil mechanics as an important consideration in environmental geotechnical practice. Now, these dams are located in the valley of the Porcellini River. It's a tributary to the Stava River. And there were 2 dams, as you can see here, the lower dam and the upper dam. And the construction of the lower dam, which was the one built first, involved placing a starter dam down here, then building it to a certain level, then building a starter dam here, and filling in behind here. And the final height of the lower dam was 26 meters. And the final height of the upper dam was 29 meters. And during the operation of the dam, effluent from the up here was carried down here and discharged out below. So the flow was from line A, where's my line A? There it is, down through there to the lower impoundment, then out through line B, this one here, out of the lower one. And that preceded the failure. Well, in January 85, a local slide occurred in the lower portion of the downstream slope of this dam right here. And there was some seepage going on there prior to that and so on. In June of 85, the line B down here, the decant pipe for the lower embankment, which had been draining everything out, it broke, and it drained all the free water and liquid mud from the lower impoundment. Well, they repaired by blocking up some pipes, installing new bypasses and the like. And they refilled everything on the 15th of July in 1985. And 4 days later, after they filled it, there was a failure that took out pretty much all of this. There was a slide of the upper dam, which pushed away nearly the entire body of the lower dam and caused a catastrophic failure. The number of deaths there was, it was several hundred, as I recall. And it was quite a catastrophe in Europe, the worst of its kind to date. Well, following the failure of these Prestival tailings dams, as you again see here, they did their analyses. There were uncertainties in properties that resulted in uncertainties in calculated factors of safety, but what they came out with were factors of safety for the lower embankment in the range of 0.92 to 1.4. They calculated factors of safety up here in the range of 0.7 to 1.3 with a mean of about 1.0. In other words, at the time of failure, the analyses that were done post-failure said there should have been a failure. So that any slight change in geometry or loading conditions would trigger a failure at that particular point where it actually took place. Well, Bertie and all, and the references given in the paper, concluded that there were shortcomings in the design, the construction, the operation of these dams. They were built without prior geological, hydrological, or geotechnical investigations, which is not a very good thing to do. Systematic stability analyses were never made. No tests were made of any of the embankment tailings materials. There was no instrumentation. What happened you can understand from the principles of soil mechanics. The problem in this case was is they weren't applied at the right time, which have obviously led to those disastrous results. We aren't necessarily always concerned with catastrophic failure or limit equilibrium conditions. We may many times be concerned simply with stress-deformation analyses. And there are situations in environmental geotechnics where these things are important. I'll tell you briefly about two things: ground movements adjacent to a slurry trench cutoff wall and landfill settlement prediction. The first is going to be in relation to a slurry trench cutoff wall. And this was a wall constructed at a contaminated site in Silicon Valley in California. The purpose was to prevent on-site chemicals from moving off-site in a down gradient direction and to prevent up-gradient off-site chemicals from moving onto the site. You know, we don't want our neighbors' chemicals on our site and they don't want ours on theirs downstream. And there was a building located adjacent to the trench that was built at this site, and deformations around the trench caused severe damage of that building. It caused them to shut down manufacturing operations. The building was badly damaged, and the inevitable lawsuit resulted. I'm going to show you more details of the stratigraphy at the site in connection with a groundwater issue that I'll talk about in a bit. So I won't do that now. I'll simply tell you that the wall at this site was 30 meters deep. It was intended, as I indicated, to isolate waste within and to prevent stuff coming in from without. The wall width was something of the order of 0.9 meters. It was a 3-foot nominal width wall. And it was 1,000 meters long surrounding the site. The technique used for constructing the wall to half its depth, down to about here, was the backhoe kind of arrangement that I showed you in the preceding slide. The bottom part was constructed using a clamshell for excavation purposes. The stability of the trenches here was maintained using a bentonite water slurry. After excavation, the appropriate depth, the excavated material was mixed with bentonite, 2% bentonite, and mixed up to about 125 millimeter slump and put back into the trench, displacing the slurry in order to make the slurry cutoff, or the soil bentonite cutoff material. And everything went along quite well in terms of building the wall, except movements of the ground adjacent to the cutoff wall occurred during trench excavation, backfill placement, and backfill consolidation. Typical inclinometer moved about 15 millimeters towards the wall during trench excavation. Here, things are moving in because you're changing the state of stress in the surrounding soil from here and here, is pushing laterally. Then, when the cutoff wall is placed, there is, because of the denser backfill, more resistant material, some tendency towards pushing the side walls back a little bit. But then you have, in the ground, in this 30-meter deep trench, you have this quite wet mixture, low slump mixture of soil and bentonite, and you have lateral stresses from here and here as the ground tends to readjust itself because of the removal of all support from the middle. It tends to squeeze in. It's sort of like a consolidation with the sample oriented vertically. It's pushing in this way. And so as this consolidates, you get some movement of the adjacent ground. There was some suggestion in one section anyhow that it was very near to failure over in a manner something like this. The upshot of it of the whole thing was, though, that the building underwent excessive distress. Now, the analysis of those deformations and their predictions is not a trivial exercise. It's a difficult problem. that is being looked at now, especially by my colleague George Fills, who wrote up this particular part of the thing for us. And was much involved at the time and is continuing research on the behavior of slurries and slurry backfills in these slurry trenches in an attempt to, through rational analysis and understanding of properties, come up with better predictive schemes for figuring out what's going to happen when you make these kinds of cutoffs. Particularly, that's important when you have structures or other developments adjacent to whatever it is you want to do. That's one example of deformations. Another, what you're looking at here, are contours of waste thickness at an existing municipal landfill in Massachusetts. And this landfill is to be expanded vertically to accommodate this disposal of up to 27.5 meters of wastewater treatment plant sludge. This is written up in a paper at Geo-Environment 2000 by some of you who may, known to some of you who were either at Geo-Environment 2000 or have the proceedings, ASCE special publication. It was written up by Stolgis and some of his colleagues in that particular volume. And the idea then was to pile this sludge, additional 27.5 meters. And their concerns were, how much additional settlement is there going to be in this municipal waste landfill? We need to know that because we have to design leachate collection and removal systems and gas collection systems and all of those kinds of things. And if we don't do it right, these things will all get torn to bits. And so these are the contours of the existing waste. Test fill. One of the ways that they got information about the compressibility of the waste was by means of a test fill. And from the test fill, they got these settlement contours, or these settlement patterns, as a function of time for different parts in the fill, and these contours at different times, 10, 18, 20-something, 99 days after putting the load on the test fill. This provided some field test information about the time rate of settlement of this municipal waste landfill under loads. And it showed the contour distribution across the landfill. With the aid of that, they were able to make predictions using a settlement model that was developed by Jarngard and Edgers, and basically is a loading accompanied by a primary compression, secondary compression, and the like. And you can do an analysis that is fairly classical in soil mechanics work of figuring out settlement as a function of time, using the parameters that they derived from the field test results. And in that way, they were able to make predictions, and you can see that these are the settlement contours that they worked out on the basis of the methodology that was built onto that settlement model that I showed you in the earlier slide, predicting these many feet to ultimately take place. And the output of all that was guidance for them to be able to go ahead and work out the design schemes then for the collection, removal, gas systems, and all of those kinds of things that we needed, or they needed. Okay. Now I will show you two examples of seepage and contaminant transport and their important role in environmental geotechnics. There's an interesting aspect when you get into seepage here. If you think about a lot of the work we do, we get very much concerned with seepage quantities. We need to know about pore pressure distributions and the like. Often this is for analyzing dewatering issues or perhaps the leakage through a dam or whatever be the case. And we are very often forced to deal in terms with quantities to the nearest, say, half an order of magnitude, because of the great uncertainties in predicting hydraulic conductivities and flows in real situations. It's a very difficult problem. And we can live with that in many cases. The problem when you are confronted by some of the environmental problems is that if there are contaminants being transported from one place to another, you may be looking at things, concentrations of parts per million, parts per billion, to satisfy some sort of a regulatory thing. And you have to try and be much more precise in what you're calculating and estimating. I'm not sure that we really can be much more precise, but you at least have to try to know your properties better and better model what all is going on. The next point I want to make with respect to the seepage and contaminant transport is that diffusion through waste containment barriers may be a very important component of contaminant transport. We have to broaden our traditional soil mechanics way of thinking of just the advection, which is the contaminants carried with the flowing water, to include also the diffusion, which is the chemically driven flow, because it can be important. And I want to show you a case that indeed illustrates this. This is reported by Quigley and Rowe and some others in related papers working out of the University of Western Ontario. And they analyzed what was happening at the site where domestic solid waste had been placed over a massive gray clay, which was the bottom seepage barrier at this particular location in the Sarnia, Ontario landfill. And the properties of the soil down here are shown. You can see plastic limit, water content, liquid limit, pre-consolidation pressures, and all of these kinds of things, pressure distributions, and the waste is piled up in here to a depth of, I think it's 7.5 meters. And the important thing is to note the migration of salts from that waste by diffusion, which is shown over here in comparison with what was transported by seepage, just moving with the seepage front. The hydraulic conductivity of this material was something of the order of 1 times 10 to the minus 10 meters per second. And so after 12 years, you could figure out that the seepage would have extended down to something like right there, and after 100 years, the estimated seepage would have gone to about there. But look at where the chemicals had gone. They'd gone way on down here. This happens to be chlorine and sodium that they were tracking out of that landfill, and you can see that the concentrations have migrated way on down. And the reason for that at this site was because of chemical diffusion, which was moving faster than the actual fluid flow. It's an important consideration when we deal with barriers, because with barriers we need to have hydraulic conductivities that are down there less than, say, 1 times 10 to the minus 9th meters per second. And that's the range where your diffusion starts to become very important relative to the simple advection. The second example under seepage is that relates to our wall back in the Silicon Valley in California. Remember, that was put in there to cut things off, as you can see here. These are aquifers and aquitards, and the wall was intended to cut off the seepage that was passing through the A aquifer and the B aquifer right here. And in the paper itself, for those of you who might be interested, there is a typographical error on page 20, I think it is, down about a third of the way down the page, where I used the word aquitard when I should have said aquifer, the A and B aquifer. In any event, the wall was constructed then to cause a blockage of the flowing groundwater here. They lowered it some in here by groundwater extraction. The damaged building actually sat right here. That damaged building we looked at right before here. There was another building over here. It wasn't damaged much at all. But among the things that happened was one of the things that was intended was to isolate things. So the case here illustrates the importance of groundwater seepage and the impact that the complexities in stratigraphy and the geohydrologic conditions can have on contaminant transport. And we need to keep those kinds of things in mind. And these are sort of the bread and butter kinds of things that come out of our traditional soil mechanics and how we apply it to problems. We need to use good mechanics in solving the problem. Well, the last category of examples that I wanted to show you were those for geo-environmental projects in seismic areas. As John Louis indicated in his remarks earlier this afternoon, here we have lots of expansive soils, and they are getting attention, as rightfully they should. They don't get the front page news, though, that does something big and bad in a seismic area, because there is indeed loss of life often associated with it, And with earthquakes, there can be catastrophic failures, and so they do get a lot of attention, including landfills. They are written into some of the regulations for municipal, it's subtitle D of the RECRA regulations for the design, construction, and operation of landfills. And sometimes these kinds of things have to be taken into account when dealing with building a landfill, evaluating a landfill, closing a landfill, and the like. And so these are the kinds of problems that come up, both with landfills. They will come up also with tailings dams. And they're the kinds of things that modern geotechnical earthquake engineering analysis can be helpful for. And we're going to look at two examples very briefly. First, the analysis and performance of the landfill, and then the seismic liquefaction of the El Cobre tailings dams, a very interesting early case of a tailings dam failure caused by earthquakes. Here's that landfill back in Los Angeles again. That's the one from the response that I would like to talk about from the response analysis standpoint. This is 300 feet high. It's the OII landfill. It's in Monterey Park, California, which is sort of in the central area of the Los Angeles region. And here's a freeway. There is concern about an earthquake that could cause stuff to land on the freeway. There is another area where there is a buttress wall with a residential area at the bottom. There's concern about that. It's a Superfund site that needs to be closed permanently, and a cover needs to be placed over this whole thing, a suitable approved cover. And so a lot of work is going on with this particular landfill at the present time. It contains some 27.5 million cubic meters of municipal industrial liquid waste, soil cover layers to waste and cover layers down to a depth of about 100 meters. And among the things that have been done is to back calculate how this responded in both the Northridge earthquake in 1994 and the Landers earthquake in 1992. The Landers earthquake was a 7.4 magnitude. The Northridge was a 6.7. One of the problems that we have in dealing with these things, we don't know the properties of the waste properly to do the response and so on. So people have back calculated what is going on to try and figure out how the response will really be and then compare it with the way that it really was. And these are some properties that were used for the analysis of the seismic response of the OII landfill. It's taken from a paper by Kavazanjian and Matasovich, written in 1995. And this is simply the depth and the unit weight depth relationship. This is the shear wave velocity as a function of depth. This is the modulus as a function of shear strain, and this is the damping as a function of shear strain. All things that one needs to do in order to make analyses. The significant thing of their analyses were that by taking the earthquake response spectra, which happens to be the solid line, I believe, for these two earthquakes, and doing the calculations, they could reproduce reasonably well what happened. Now, what is learned by doing that is that by the assumption of reasonably correct properties, we can predict reasonably what went on. That gives you confidence for extrapolating now to other cases, to other landfills and so on, because we have, in a sense, validated some of the methods and some of the assumptions that have been used. And Matasovich and Kavazanjian here were able to draw some conclusions that are helpful in making that step, because we simply don't have a large amount of data on these properties. And this is how they're helping to build our repository of information by using back analyses. And among the things that were found were that there was amplification of the ground motion. One of the things that we like to look at when there are earthquakes is, well, how did the ground respond, the ground acceleration, for a given bedrock acceleration at a particular site? That has a tremendous impact on how structures fare, like landfills or buildings or bridges or anything else. Because we know that under some conditions, the rock accelerations, looking right here, for example, at point 1, if the ground surface acceleration would be the same, would fall on this line right here, But in Mexico City in 1985, and Loma Prieta earthquake in 1989, the 1979 Montenegro earthquake here, and so on, these zones are all above this line of equivalence 1-to-1, which means that the ground has amplified the shaking. So it shakes much more up here than it does at rock, and that has severe consequences for the structures. And what they found in looking at the landfills were that the landfills are up here equally well amplified. So that needs to be taken into account. The landfill can amplify things. Certainly this was true, not at a different kind of landfill, but in the recent Japanese earthquake in Kobe, the hydraulic fills that were placed for artificial islands and the like really amplified the ground motions to the point of liquefaction. Now the last case is that of the dams at El Cobre, and this is a rather old case history. And it's something that happened in 1967, 1965 actually. It was the earthquake in Chile. It shook in the provinces of Aconcagua, Valparaiso, and Santiago in central Chile in March of 1965. And most of the tailings dams in that region failed. And there were two dams at El Cobre where the failure was particularly devastating, and 2,400,000 tons of tailings flowed out, traveled about 12 kilometers in a matter of minutes, destroyed part of the town of El Cobre. It killed more than 200 people. And in 1965, there really wasn't much seismic design of dams. Not too much seismic design had been undertaken at that point. It wasn't a developed part. Since then, a lot has gone on. And more recently, of course, we pay a lot of attention to this. Well, tailings have been deposited there since the 1930s at El Cobre, and they used the gravitational method. I think, well, let me back up one. They deposited the tailings in the downstream crest of the dam. They didn't use a cyclone. They allowed the material to flow upstream. They had methods that are no longer used so much. And the back analyses tell why these kinds of things are no longer used so much. It's just not a good way to build a dam. But 3 dams were constructed at this site, and 2 of them, the old dam and called the old dam and the small dam, were built between 1930 and 1963, and they accelerated the filling by the end of that period, and they built the 3rd dam, called the new dam. It was constructed between 1963 and the time of the failure. And the earthquake caused 2 of the 3 dams to fail completely. And the fill at the new dam had been placed within a year and a half, and it was just beginning to consolidate, but it hadn't consolidated enough. And so the shaking was enough to cause the failure. Well, a post-failure investigation was done at one of the dams. This was the small dam, the one that didn't fail. But the kinds of materials that they were dealing with, unconsolidated tailings, a dry hard crust and the like, and old tailings down here, firmer ground down here, you can see that the standard penetration resistance was really quite low. And this was pretty fine grain in through here, in this weak zone, and this just tells you something about the moisture content. But the general nature of the failure was that you had a structure that looked like this, something that looked like this, and after the earthquake, it looked something like this, with horizontal terraces and scarps and so on as the material flowed away. This was analyzed by Dobry and Alvarez in ASCE in 1967. It's an excellent paper describing all of this. And they were very ahead of their time almost in trying to analyze this thing. They used a technique which maybe by today's standards would look a little bit crude, but I think it pretty well captures what they concluded went on. The seismic horizontal accelerations gave you an inertial force within your potential failure material. There also was material that had tended to liquefy back here, giving you an additional horizontal thrust on this, and put together that whole thing would cause it to fail. And while maybe crude compared to a modern-day dynamic deformation analysis, nonetheless, from a limit equilibrium standpoint, explains very nicely what went on. And this kind of thing is usually done in some form or other, even in modern analyses, before they get on to the involved dynamic deformations. But the ability to do stability analyses, figure out which are the forces and where they act, is an important part of doing all this, and of course, that is soil mechanics. And what strikes me as interesting about this is the similarity between this kind of a topography and what was observed both at the Turnagain Heights landslide failure in Anchorage, Alaska in the 1964 earthquake, and at the Lower San Fernando Dam failure in Los Angeles in 1971. A lot of similarity between those two things. And this was one of the pioneering studies that was done to get people started looking at those kinds of failures. So that gets me to the end of the cases and essentially to the end of the presentation. And I have just listed here a few conclusions, all of which are still trying to say the same thing in these environmental geotechnical problems. Soil mechanics plays an important part, and we need to do the best job we can, along with our site characterization and our materials characterization, to get answers that will guide our judgment, enable us to make decisions that will be suitable to do safe and lasting projects. And I've listed a few more specific points here. We have demanding criteria for these things. There are regulations, and we have to deal with them as best we can. We have to understand our stability, our seepage, our deformations, and our settlements. And the principles of soil mechanics and waste mechanics, geosynthetics mechanics, it's all part of the same thing. They're all quite applicable. We have to give special attention to the properties of dissimilar materials. And I think that one area in which we haven't done enough in our work to date is right here, biological factors. We start talking about it in clogging of collection systems and drainage systems, all those kinds of things. We get into the decomposition of waste and the associated settlement. We might get involved with some of those considerations. But in a serious way, I don't think many of us in the geotechnical field have looked at the importance of biological influences on our materials and on the properties with which we are dealing. So that's what I wanted to say to you about the role of soil mechanics and environmental geotechnics, and I thank you for your patience, and I'll be happy to try and answer questions. Thank you.
Okay, it's open for questions. Do I hear any questions from the floor about the presentation? We've captured good Professor Mitchell here, and let's take advantage of it. We'll let Jean-Louis break the ice.
Well, if you had to develop a geotechnical graduate set of courses for the 21st century, would you create some separate courses addressing environmental geotechniques, or would you try to incorporate these aspects in the existing courses?
I suspect, John Louis, that I would try and do some of both. I think that it's always useful to incorporate current and anticipated problems within a course of anything. Okay, and certainly being as dominant as it is in our field today, and will continue to be, environmentally related issues and problems should be in what we might call more traditional courses. But I think there are some things that are sort of unique to the practice of environmental geotechnics in the same way that soil dynamics, let's say, is essential to geotechnical earthquake engineering, that you'd want to have some focus courses as well.
Okay, another question from the floor? Yeah, Bill Johnson. Identify yourself if you would. I recognize Jean-Louis, but Bill, if you would introduce yourself.
I'm Bill Johnson. I'm a graduate of Texas A&M, and I have practiced geotechnical engineering for a while, but I have a question that's bothered me about the landfills that we're doing today. Biological degradation takes place in the presence of water, moisture. We're building our landfills so that no moisture ever gets into it. So then we cannot expect biological degradation to go on. What, we have something out there that's, that is a compressible mass, can be degraded in the presence of water, but we provide no water to it. So that bothers me, that we are building something that can never change and can never go back to the environment.
I think many of the municipal waste landfills, past and present, will have some moisture in them because of the nature of you know, the garbage and the vegetation and so on and that type of thing that is disposed. That's the material also that will break down biologically. And if there is air, well, you can have decomposition both aerobically and anaerobically, generating either carbon dioxide or methane, depending on which the environment is. And that can certainly take place. In fact, I think in some landfills, they are actually accelerating some of the decomposition by deliberately injecting air. So that if there is some moisture present, then there will be there can be biological decomposition. If there is no moisture present, where has it gone from the stuff that would be there to decompose in the first place? You see. So I don't have a really perfect answer for your question, but I think it might not be too much of a problem. There's a couple more. Another question.
Jack? Jack Burke from the school here in Providence. I had a question about Kettleman landfill you mentioned there, Professor. Somewhere in there you showed some instrumentation, but it's very common, as you know, for dams and tailings to have a lot of instrumentation for major projects. Was there a lot of instrumentation preceding an early warning to that large landslide? Was it the Kettleman?
The Kettleman was the failure that I used as an example. There was not a lot of instrumentation in the fill or in the surrounding ground, but there were a lot of careful measurements. So we knew in great detail about wherever a piece of geosynthetic was, what the orientation of all the grids were, or which way they unrolled the rolls. We knew all that kind of stuff. We knew the quantities of waste and where they were placed. And so there had fortunately been a survey flown of that waste pile within 4 days of the failure, so we knew the topography pretty well. So in the sense of having survey information, there was a lot of information. But as far as having information about movements within the waste, we did not. There was information about leachate production rates and so on that was available as well.
I've got a question about that one too. Was that owned by an industry or was that a municipal owned?
No, that was built and operated by a major waste company.
Okay, so they had the failure and internally they solved the problem as opposed to being a lawsuit.
Oh no, I can't say that it was. Remember, there were designers and builders and the owners and so on. So there was a settlement. The owner wasn't content to let the designer just go scot-free because it failed, or after it failed.
Well, it seemed that the two-dimensional analysis you said was quite different from the three-dimensional analysis. Certainly enough to cause failure, just a difference in analysis.
Let me correct that. I'm not saying that it was enough to cause failure. I think piling the waste as high and as deep as they did caused the failure. Analyzing it to be, to bring your factors of safety to 1 at the time of failure, or even low enough below 1, so that you could account for the movement that take place, required a careful examination of the real geometry of failure. And the understanding of the 2- and 3-dimensional behavior was very important in this, but it wasn't significant enough to say that had they done a three-dimensional analysis correctly, and I doubt they could have done it because it hadn't been worked on at that point, I don't think that would have made the difference. It was simply, in my opinion, not having a filling plan and having done stability analyses that would tell you what's going to happen when the waste gets this high. It was perhaps a failure to recognize what could happen.
Well, it just seemed like was it 100 meters?
No, I was 100 feet. Yeah, about 30 meters.
Well, with the two-dimensional analysis that they would have used, I presume, since it wasn't previously used, would it have worked at 100 feet of fill with a two-dimensional analysis?
Well, again, it's sort of subjective, but if you go in as people did immediately following and tried to draw what you think is the most critical two-dimensional failure section, and looking at that and plan, I don't know what you choose, but supposing you choose where the waste is the deepest or whatever, you come out with a factor of safety that is much too high.
More than one.
Yeah, more than one. Yeah.
Any other question? Yes, he had his hands up.
Jim Yao from Texas A&M. I'm just curious. I really enjoy your lecture. You know, a lot of new information, and I'm just curious if you could advise us on how to improve our civil engineering undergraduate curriculum. You know, so that our students can get benefit of all these studies and be flexible when they graduate. And at the same time, you know, we still have to teach all the other fundamental things. Would you please advise us on how to improve?
Yeah. Thanks, Jim, for an easy question. At what time is dinner being served? Well, you should be able to answer that, having just chaired this very successful ASCE education conference this past summer. I thought you would know all the answers, but I don't know. You know, I can give a personal opinion, and that is that if we want to look just at the technical side of it, and I might have something else to say on the professional communication side, of course, but looking at the technical analytical side, I would say, emphasize the basic, maintain strong emphasis on fundamentals, create people who can think, because you don't know what tomorrow's problem is going to be. Don't allow too much specialization. Some learn how to do at least one thing well in depth, whether it's to design the members of a bridge or to do stability analysis of some sort of a problem, or to design a transportation element of some kind of a thing. Sure, get that kind of a depth, but in my opinion, the worst thing that one can do is, in the name of flexibility, give a wide open curricula where somebody can choose all their own courses for themselves and take 10 elective courses in structural design, and then 2 years after they graduate decide, I don't like that very much. They have no place to turn. And because of that, and because of our inability to predict the future, who was it? Was it Niels Bohr that said predictions are very difficult, especially about the future? We don't do it well. We don't do it well. And how else can you adapt? And I think the person who knows fundamentals, okay, understands Newton's laws, Terzagh's effective stress, whatever, okay, principle of ritual work or something, and can think laterally. Someone who can say, gee, this is a seepage problem for which I don't have a solution, but somewhere in my heat transfer I saw something similar to that and realized the mathematical solutions for those two problems are the same, exactly the same. You just change the input parameters around a little bit. That's the way that you can begin to address those things in the future. The best products are made from the best raw materials, right? And so you hope to have good applicants who come from programs perhaps about which you know something and you have a good sense that they're going to be able to grasp it. But there are always other things that come in, particularly at a place like Berkeley now where funding is limited. You can't offer a lot of scholarships and so on, so that immediately says, well, we just can't take many people in this category who don't have support, no matter how good they are, because the number of fellowships is limited. there was or there is a certain minimum grade points and, you know, letters of recommendations, all the usual procedures. But I think to a large measure, we were successful there because we had just had good applicants. And I think the way you get good applicants is to have a good program, you know, and one feeds the other. You know, one feeds the other. So,
We'd like to present you, Jean-Louis is responsible for this. We'd like to present you with this plaque commemorating the fact that you were the third Buchanan lecturer. And along with it, of course, goes the honorarium.
Oh, well, thank you so much indeed, Philip. It's been a pleasure. Thank you. Thank you all.
I don't think we're going to have any lack of problems to work on in the near future. Jean-Louis?
But I want to thank you all for coming. I wish you good health and have fun for one more year, and I hope to see you next year at about the same time. There's a reception in the Great Hall, and I hope that everybody can stay for at least about 5 minutes, because we're going to take a picture of everybody on the staircase that is right out there. And that staircase was load tested last year, I think up to about 120 people. And I'm afraid we've beaten that record today. So, and I can't tell you what the factor of safety is. But anyway, let's try it. I guess I'll be responsible if something happens.